object na nagre-resist para mag-accelerate itong ating system. Okay? So, let's go, no? Basically, ang moment of inertia pala mga bis, no, is denoted by the letter I, no? And that's equal. Moment of inertia is equal to the mass of the object multiplied to the r. R is the perpendicular distance of the object to the axis of rotation squared. Okay, so basically guys, when we have our object here, no? Tapos andito yung axis of rotation, siguro nakakabit dyan mga bis, no? Ang M natin mga bis is kung ano yung bigat nito, ano yung mass nitong ating object, at ang ating R is kung anong distance from this point to this point. Dapat perpendicular yan mga bis, no? Yun yung ating R. So, yun lang, basically, yun lang talaga yung formula na kailangan natin mga bis. Wala nang iba, no? So, kapag hinahanap yung...
and that is because torque is defined as the cross product between the radial distance from your axis of rotation and the rotational force being applied. So these are both vectors. So let's take a look at how I taught you vectors the first time, and then I'll show you how that's really the same thing as what we're doing here with the cross product, except now with the cross product, besides just the magnitude for torque, we're also getting the direction. But then we'll also see that that direction is a little bit, it's just kind of the definition of the direction of torque. I don't know how intuitive it really is. But what did I teach you before about torque? Well, I said if I had let's say I had some arm, let's say that's the arm, and let's say it's I don't know, this could be the hand of a clock, or it's pinned down to the wall there, so it would rotate around this object. And then let me switch colors. The magenta is getting a little obnoxious. Let's say it's some distance r from
ikot. Let's go. So, ayun mga bis, no? Kung sa ating mga past videos ay napag-usapan natin ng tungkol sa mga motion in straight line, ngayon naman ay pag-usapan din natin yung pagpapaikot-ikot na motion, no? So, ayun mga bis, no? Simulan natin. 'Di ba sa ating linear motion, no? Kunwari meron tayong straight line kasi nga linear, 'di ba? Tapos from this point to this point, ang mini-measure natin diyan, mga bis, is yung displacement, 'di ba? Yung x, 'di ba? So, ayun. Tapos, kung gaano siya kabilis from dito hanggang dito, yun yung tinatawag nating velocity, di ba, mga bis? Tapos, kapag gaano bumibilis yung speed niya, yun yung tinatawag nating acceleration, mga bis, di ba? So, yun yung basic concept ng linear motion. However, mga bis, sa rotational motion, medyo the same lang yan. Pero sabi nga natin, no? Sabi nga natin, mga bis, rotational, umiikot siya. Kapag umiikot, merong circle, no? So, mag-drawing tayo ng circle.
Static equilibrium problem is to identify all forces with their locations. If you accidentally leave some forces out, you could end up getting the wrong answer. And this is the same as when we had force diagrams back in motion in 2 dimensions. Don't forget your pivot point forces. Sometimes there are forces holding a particular pivot point as a fixed point, and there's got to be forces to do that, even though we may not think of them as being applied forces at that point. After you know all your forces, then we can construct our force equations. Then we construct our torque equation. You have to do some algebra, plug in your numbers to do the math, and as always, check your answer when you're done. Now I'm going to show you an example here of just part of.
If we wish to calculate the net torque, it's equal to the change in the angular momentum divided by the change in time. Now, both equations can come from Newton's second law. This comes from Newton's second law of motion, which states that the net force acting on an object is the mass times the acceleration. And this expression comes from Newton's second law as it relates to rotational motion, which states that the net torque acting on an object is equal to the inertia of the object times the angular acceleration. Angular acceleration is the change in the angular velocity divided by the change in time. And momentum is inertia times omega. So the change in momentum, that is the change in angular momentum, is the inertia times the change in angular velocity. So therefore we can replace I times delta W with delta L. So thus we have this expression. The net torque is equal to the change in the angular momentum of a system divided by the change in time.
Okay, so let's go ahead and plug the numbers and go. Force of attraction is equal to G, and in this case we said G is equal to 6.67 times 10 to the negative 11, and that's newtons times meters squared divided by kilograms squared. And we're going to multiply that by this other quantity, mass 1 and mass 2. We'll do those in red. And mass 1, we'll call this mass 1, and we'll call this mass 2. Mass 1 is 100 kilograms times mass 2, which is 210 kilograms. And we're going to divide that by the distance squared, and let's do that in blue. And that is 4 meters. So 4 meters, and we have to square that guy. So let's simplify that. F equals, we'll go 6.67 times 10 to the negative 11. That's newtons times meters squared.
Should be less. So I'm going to go back to slow motion. I'm going to pause this, get this at the top. So this is at positive maximum displacement. Start our stopwatch and find out what's the period of oscillation here. So I'll go ahead and hit play. And advance this all the way up to the top. And we can see if we look at our stopwatch, it took about a half of a second for this to go from positive maximum displacement all the way down and back to positive maximum displacement. So the period of oscillation is about 0.5 seconds. Well, let's look at the slider, which we called frequency. The frequency is 2. So what is it about this periodic wave? I'm going to go back to our normal speed and let this thing roll. If it takes about a half of a second for any part of the material to go through one complete cycle
happening here. So let's think about where, let's say it emitted a crest of its wave exactly 1 second ago. Where is that crest going to be now? Let's think about the stationary character. Well, in this guy, it emitted the crest 1 second ago. It's moving outward. So this is outward. It's moving outward radially. I need to give a direction if I'm giving a vector quantity. So it's moving outward at 10 meters per second. So if it emitted it 1 second ago, it's going to be 10 meters radially outward from the source. So maybe that is right over there. It looks, oh, let me draw it a little bit neater like that. Let me draw it a little bit neater. That's pretty good. So that's where that crest will be. Now, what about this guy? Where's the crest that this guy emitted 1 second ago? Well, you might want to just draw a radius 10 meters